Hello ma'am, thank you for being here with us today. Before we start, I am Soraya Akhtar, CSA 2509085, representing Group 5. My other group members are Ayub Hisham, Javed Kashif and Yun Ming Xuan. So, we are excited to present polar coordinates application measuring the area covered by a radar system using polar coordinates in Calculus 2. So our key task is to calculate the area scanned by a radar beam. A radar is installed at a fixed location. It is scanned outward up a maximum range r and only covers a certain angular region theta. Our basic assumption is explain why polar coordinates fit radar coverage, build a mathematical model using r and theta, drive the area formula using calculus 2, solve on work example and interpret the result. So, knowing the covered area supports safety, monitoring and cost-efficient design. It helps engineer to decide radar location, scanning angle, detection range and whether extra radar units are needed. So, some example is airport radar, monitor aircraft around runways and airspace, weather radar, estimate rainfall and storm coverage zones, marine radar, detect vessel, coastline and obstacles, and urban monitoring, support traffic, security and emergency response. So, why polar coordinates? Cartesian coordinate describe a point using x and y, good for rectangular movements, but radar beam travels a certain distance r in a certain distance theta. Polar coordinates r theta describe this far more naturally, matching the actual physical behavior of a radar beam. Our variable A for covered area, R for maximum range, theta for scanning angles, and alpha beta for starting and ending angles. Our assumption radar is located at the origin. Radar is constant in the scan direction. Radar region is treated as a circular sector. Obstacle and single loss are excluded in the basic needs. The area is found by adding up many small sector slices through integration. Alpha beta mark the start and end angle. R theta gives the distance from the radar at each direction. The R square terms appear because area grows with the square of the radius. The integral sum all the teeny sector slices into the total area. There's a theory behind the model, but a formula only tells half of the story until you actually run the numbers through it. The rest of this presentation will handled by my other group members. Right now, Ming Xuan is coming up to take us through the actual calculation and bring this number to life.
Hello everyone, my name is Wu Xuan and my student ID is CST2509045. Let's now move on to the mathematical derivation of the radar coverage area. We'll start with the general formula for the area in polar coordinates, which is 1/2 of the integral of the square of the radar function from angle alpha to beta. In our radar model, we assume the maximum detection range is constant, regardless of the scanning angle. So we set r of theta simply as capital R, which is a constant. By substituting r squared into the integral, we can easily pull the constant out. The integral of d theta from alpha to beta gives us delta theta. Therefore, the area simplifies to 1/2 r squared times the difference between beta and alpha. Here, we define the total scanning angle, theta, as beta minus alpha. So the coverage area equals 1/2 r squared theta. And please pay close attention here. Since we are using calculus, this angle must be expressed in radians, not degrees, for this formula to hold. Now let's verify our calculus results using a simple geometric approach to ensure our model is consistent. We know the area of a full circle is pi r squared, and its corresponding full angle is 2 pi radians. Our radar scans only a sector of this circle with angle theta. Geometrically, this sector is simply a fraction of full circle, specifically theta divided by 2 pi. If we multiply this fraction by the total area of the circle, the pi cancels out, leaving us again with 1/2 r squared theta. As you can see, both the integration method and the traditional sector geometry yield the exact same result. This confirms that our mathematical model is physically and mathematically consistent. Thank you.
Hello everyone, my name is Hisham Hussein, and today I'll be talking about applying the polar sector area formula to a realistic radar setup. So for this worked example, we're applying the polar sector area formula to a radar coverage problem. Say we have a radar with a maximum range R of 60 kilometers scanning from 30 degrees to 150 degrees. That's an arc width of 120 degrees or 2 pi over 3 radians. First, we convert those angles to radians. Alpha is pi over 6, beta is 5 pi over 6. Next, we apply the general polar area formula, a half times the integral of r of theta squared d theta, where r of theta is just our constant range r. Since r doesn't change with angle, that integral collapses down to a much simpler formula. A equals a half r squared theta, where theta is just the angle swept beta minus alpha. This is really just the familiar circular sector area formula, half the radius squared times the angle. Plugging in our numbers, a half times 60 squared times 2 pi over 3, which simplifies to 1800 times 2 pi over 3, or 1200 pi square kilometers, left in exact form. We'll evaluate that on the next slide. Okay, now let's substitute in the numbers and see what that means in context. A half times 60 squared times 2 pi over 3 gives us exactly 1200 pi square kilometers, which works out to approximately 3769.9 square kilometers of scanned area. To put that in perspective, a full 360 circle at that same 60 kilometer range would cover about 11,309.7 square kilometers. So our 120-degree radar sector covers roughly 33% of that, which makes sense since 120 over 360 is exactly 1/3. That's a nice sanity check for that our calculation is correct. Okay, let's go to the next slide. So what do these numbers actually tell us about the radar design? First, range dominates because area scales with r squared. If we double the range to 120 kilometers, the coverage area doesn't just double, it quadruples to about 15,079.6 square kilometers. That means range upgrades give the best gains in coverage, but they are also expensive to build up. So the angle, on the other hand, scales linearly. Widening the scan from 120 to 180 degrees only increases the area by 50% to about 5,654.9 square kilometers, a much smaller payoff than extending the range by that same proportion. In practice, a directional or sector radar is more efficient. It uses less power and costs less than full 360 degrees coverage, which makes sense when threats or traffic mainly come from one direction, like a runaway approach or a coastline. Thank you.
Hello, my name is Kashif Javed, CST 2509098, and I will be talking about the practical implications or how these calculations are used in the real world. First of all, it helps with radar placement. Radar placement, where by calculating the exact area, we can estimate whether just one radar is enough to cover like our specific zone, like for example, in an airspace or a coastline. Secondly, it's important for safety coverage because knowing the area that the radar covers helps us identify blind spots in places like airports, roads, and it helps address safety concerns in terms of weather before they actually cause a concern. Finally, it helps with cost planning and design testing. So instead of buying and installing expensive radar equipment Engineers are able to test different ranges and angles on paper before they buy the radar. So this allows them to compare whether it is better to get a wider angle or a longer range or just to get a completely new unit. We move on to the limitations and possible improvements. Right now, our basic model that we have just gives us an ideal maximum coverage, but not the exact reality, because in the real world, physical obstacles like building, hills, trees, they can block radar signals. Also, bad weather can interfere with radar signals. So, to fix this, we have just made a few improvements to make the model better. So instead of keeping the range constant, the model you can see below, half multiplied by the integral of alpha to beta of r theta squared d theta. This enables us to combine the map with city maps. So in this sense, it will include any bad terrain and signal loss, which makes the model much more realistic. To conclude our presentation, radar coverage is naturally shaped like a circular sector, which is why our polar coordinates fit this behavior perfectly. Secondly, we used our area formula to derive this sector formula, A is equal to half r squared theta. In addition, in our example, we were working with a fixed range of 5 kilometers and a 90-degree angle, and so the total covered area came to approximately 19 to 20 kilometers. And lastly, our graphs prove that changing the angle has a direct linear effect on the area, but changing the range, however, has a much stronger effect on the total coverage. Thank you so much.